Okay, will you do me a favor and check your homework? So I'm just going to take a minute and scroll through this. Since I am making this recording, I'm going to scroll through, mark what you have issues with, and then I'll go on to a Smartboard file. So here are your first set of problems, 1 through 13, you can see. Yes, so it'll help, yeah, if you get your homework out. And if you glance down and compare to the answer key, there you go. If you're up all night, you could have done it. Okay, can I scroll? Okay, here's the next portion. Next portion. Can I keep going? Ready? We're going to the back. You need me to slow down, Eddie?
Wait, what's 15?
Okay, on the back. So this was the last thing we talked about, numbers 23 through 26 there. What was what? 4. I'll scroll back up. Everyone check 23 through 26? Okay, so here was 4. There you go. Okay, so in a minute, we're going to actually look at the application questions that tie in with matrix multiplication, but we don't want to do that until we can make sure that we are fully fine multiplying. So, does anyone have any problems that they want to go over? Yeah, Madeline? 9. Any others besides 9? We'll put on the list. Addie? 9 and 15. Okay. Yep. Okay. No. You would get most credit for it, but we'll fix that. Okay. So 9 and 15. Let's rattle those off real quick. So number 9. Gives us 3 times the matrix C, which is 3, negative 3, negative 1, 2, negative 2, 4. 3C minus 2. And then it says DC. So you got to be real careful here. D is 1, 0, 0, 1. And C, I'm going to squeeze it in, but then we'll spread it out on the next one, is the one we just wrote down. 3, negative 3, negative 1, 2, negative 2, and 4. On the next line, I'll clean that up a little bit. What can we do really quickly and easily? Yeah, use this to take the scalar multiplication and have it affect that matrix. Can I get a volunteer? What's that going to be? Go, Olivia.
9, negative 9, negative 3, 6, negative 6, 12.
That's right. Okay. Minus, now, what must I also then do? I have to do this next. You could. I'm going to tell you to think of it in terms of PEMDAS. So the properties of, most of the properties of matrices can relate to properties of real numbers. So for example, if I have parentheses, exponents, multiplication, I want to go ahead and multiply this. So I'm going to take a minute and put that 2 out there. You can do what you said. I just think it's clean to first do this multiplication. So I'm going to write this out just a little cleaner so we can see it. So I've got 1, 0, 0, 1, and then I've got 3, negative 3, negative 1, 2, negative 2, 4. And now I'm going to do that multiplication. How big is this? How big is this? Is this multiplication legal? Yes, why? Middle numbers match. What will be the dimensions of the new one? 2 2 by 3. So I'm going to draw it out like that. And while your final answer can never include these lines ever, I do think it helps if you kind of go like this, so that I know I have 2 rows and 3 columns. The only reason I think that's helpful is it helps you keep track of what elements I've taken care of. Make sense? And what goes where. So now I'm going to multiply these out. So I'm going to go pretty fast. So if I say something wrong, stop me. But I'm going to rattle through it. This is 3 plus 0 is 3. This is negative 3 plus 0 is negative 3. This is negative 1 plus 0 is 4. This is 0 plus 2, 0 plus negative 2, and 0 plus 4. Is everyone okay with that? Say again? Right here I put, this is negative 1. This is 4 down here. Okay? All right, so now I have this matrix, 9, negative 9, negative 3, 6, negative 6, 12, minus 2 times that matrix. All right, now what? Go, Daniel. Yeah. Now, when I multiply the 2, you want to tell me what that would be, Daniel? Okay. That 2 has gone in. What operation is still out here? Subtraction. This is then 9, negative 9, negative 3, 6, negative 6, and 12. Can I get a final answer? Someone tell me. Either do it straight from there or tell me what you got. Or I'm going to randomly call you. Go, Andrew.
3, negative 3, negative 1, 2, negative 2, 4.
Perfect. Okay? All right, 15 was our next one, yeah? 15. So, Addie, you want to tell me, did you set it up okay? Or do you know if you set it up okay? Maybe it's a better question. Okay, what's the size of the first one? 1 by 3. So this is a 1 by 3 times a 3 by 2. So it's legal. The dimensions of the new one, the dimensions of the new one will be what? No. What are the dimensions of the new one? 1 by 2. The outside numbers give me the dimensions of the new.
Okay.
So this is a 1 row, 2 column. So really it's just 2 sets of evaluations. I'm going to go, and this one's really easy because this is just 0, 0, 0, right? And then this one is 4 plus 1 is 5 plus 36 is 41. Okay, so to go back to your question page, what number were you on?
It was 20.
Okay, so obviously the process you're using is correct. The way you would know how it should be shaped or facing is in number 20, I have a 3 by 2 times a 2 by 2, right? So this combo makes it legal. This set of dimensions is the size of the new one. So I have to have 3 rows, 2 columns. That's just kind of how you can know ahead of time. Because otherwise you're okay. Okay. Yep.
When you're like multiplying those ones, do you do 3 times negative 1 and then 3 times 0? Is it 3 times negative 1, negative 2 times negative 1, negative 1 times negative 1?
Neither. You go rows and columns.
Yeah.
So 3 times negative 1, right?
Yeah.
Plus 1 times 0. This hand, my left hand has to be going across, and my right hand has to be going up and down. Okay?
I did that. I just said it wrong.
Okay. Okay. Now, what we want to do is apply this to word problems. Okay? So I want you to turn to what I believe is example 4 in your notes. Yep. Example 4 in your 12-2 notes from yesterday, or your matrix multiplication notes from yesterday. And this is where it gets really important that we understand the labeling of rows and columns and what's being multiplied to give me what. So, all I'm going to ask you to do is pair up. I should hear lots of voices. Pair up and have one person read out loud what is happening in this situation, and then if there's any matrix that you can draw at all, try it. Okay? If you can write any matrix whatsoever, try it. That's all you got to do. Go. If you need me to pair you up, I will. Meredith and Alec, you're together.
Sports in 1966, Washington and New York Giants played the highest scoring game in national football history. Playing summarizes the scoring. A touchdown is worth 6 points.
Okay, so one matrix should be really easy to set up. If you can't do anything else, you should be able to draw something. Label your columns, label your rows.
Would be like a 1 by 3. But like, how do we?
Okay, if you've got any idea what numbers are at least in one matrix you can write down, what are they? Can you give anything? Okay, so it's a real, I'm going to say something that is super sophisticated. Ready? Look at this. There are two rows, and shut the front door. Guess what? Say it. 4 columns. So when you stare at me, and don't worry, this will apply to 8th period who listens to this too, because they stare at me too. When I say, what do you see, and you literally look at me like this, or some of you go, I don't know, I can't figure out anything. Try to at least apply something that I've taught you for 2 full days. How many rows? 2. How many columns? Now see, you at least laugh. 8th period will listen to this, and they'll be like, she's so dumb. And then they'll roll their eyes, and some of them will just literally make no facial expression whatsoever because it's like lifeless. All right, so we're going to set up our first matrix, 2 rows, 4 columns. So please do so. You ready? We're going to go 10, 1, 0, 9, 6, 0, 0, 5. Okay, the rows represent what? Thank you. Good laws. So I've got Washington and New York. Now, my columns represent what? Give me words. So different ways that you can score, right? So what I said the other day was you've got to get in the habit of labeling your rows and columns. Because when I go to multiply things, I know that the columns of the first must match the what? There! Rows of the second, right? So before I even do anything, in my head I'm thinking, okay, I gotta label these, and I gotta figure out, okay, what's my next matrix gonna look like? But here's the other underlying part. It says, the question is, what was the final score? Meaning, how many points did each, now look, you know realistically, if I told you that, first of all, Washington scored an absurd amount of touchdowns, you immediately know what to do with that number, right? What do you know to do with it? Multiply by 6. So just watch for a second. You don't have to write this down, but just watch. I would normally take the number of touchdowns, multiply by how many points it's worth. And you would tell me to take the field goals and multiply by what? 3. You would tell me to take the safety, is that what that is? Yeah. And multiply by 2. And then you would tell me, sorry, this should be 0 times 2. And then you would tell me to take the number of point after touchdowns and multiply by 1, right? And then do what to find out the score? Add them. That should sound like matrix multiplication in a way. Because I do 10 times one number, plus 1 times another number, plus 0 times another number, plus 9 times another number. You with me? So as a result, when I go to set up a matrix that is multiplication when I go to evaluate it, I need to be thinking, okay, those have to line up with each other. Somehow the 10 has to go with the 6. The 1 has to go with the 3. So think about this for a second. I need the final score. I already know how to do it technically. If you're like, well, why would I do it with matrices if I can just do it in general? Because we're really like taking a large scale ability of especially technology and bringing it down to a really simple scale so that you can experience the power of what if you had a huge matrix, like a 100 by 100 matrix, and I'm multiplying those so that I don't have to calculate all those by hand. If I've got some sort of program that can run that matrix multiplication, I no longer have to do it by hand. So you're experiencing it on a really low scale. How big is this matrix? Go ahead, up.
Can
2
you
by
do
4.
this in your calculator?
Yeah, we're going to talk about that a little bit more today, especially next week. We can. Yep. So I have to multiply by something that's 4 by something. Now, okay, fine. But we just said that the columns of the first must match the what? Say it again. The rows of the second. So I'm going to start to label the rows of the second. And I'm going to say, fine, touchdown, field goal, safety, point after touchdown. Those better match. And my end result, now watch this part, must be a final score, right? A score for both teams. So therefore, if this row ends up here, which it should, right, as a dimension, we already said this is a 4 by something. 4 by what? 1, because I'm going to have one score for each team. But what does this column represent? What does that column represent?
Points.
Yeah, the points. Yeah, if you want to put points here, you just need the words to match, right? So if that makes more sense, you put points here and then put points here. But now notice, this is not just a 2 by 4 times a 4 by 1. This is and this should always match for you. This is a team by, we'll say how we score, times how we score by points. The middle must match, and the outsides are your dimension. Make sense? Okay, so we're going to put in those values that you told me. 6, 3, 2, 1. Find the final score with your groups. Go. Just pop your hand up when you have an answer. There's not a lot of defense happening in this game. Got an answer? Okay. So, Joey, what'd you get?
72-41.
Agreed. Okay, we're all right? Part of your homework tonight is going to be to practice that, and we'll talk about that more when we get to it. Okay? All right, so what we're going to now do is go to our new set of notes. And what I'm going to ask you to do is we're going to skip over this warm-up. We're actually going to use it tomorrow. I'm just going to take this quick moment to remind you, we're going to have a quiz over everything you learned this week on Tuesday. Okay? So tomorrow, what I don't get done with today, I'll finish. But then we'll also just have time to work and practice. And some of it you barely need practice on because it's super easy. Okay? But the harder stuff we'll practice in class tomorrow. So for now, we're going to skip this word problem. And if you would for me, jump to this slide. And all I want you to do is take 30 seconds, totally just read it to yourself. One question I'm going to quickly ask is, what does it mean to be a square matrix? also going to ask you, what does it mean to be an identity matrix? And then if you'll just look up here when you're done reading, so I know you're done. Okay, a square matrix is one that has what? Same rows, same columns. That's right. Okay, that's part one. Part two, it then goes on to say that a square matrix sometimes has a what? Sometimes has an inverse. Okay, so I want you to think, if you remember yesterday, we looked at the properties of matrix multiplication. And we said the difference between addition and multiplication is there was no commutative property, right? Everyone remember that from yesterday? So can you just randomly swap the order of two matrices and get the same thing when you're multiplying? No. When you're multiplying, the commutative property does not exist. You could, but you may not always. And typically you don't. Okay? That's part one. But someone brought it up, I kind of skipped over it yesterday. The second property, not on the multiplication list, that was on the addition list, was this issue of having an identity and an inverse. I'm going to remind you of what the additive identity and additive inverse is. If I have a matrix plus a bunch of zeros, what do I end up with? The original matrix, right? So we called the zero matrix, we called it the identity. Why? Because if you multiply by it, you get the same thing. You with me? Then we said if I take a matrix and add all the opposites, what do I end up with? The zero matrix, right? Why? Because those two identities are considered inverse matrices of addition. Well, we're going to need that to occur for matrices. So this clarifies that, hey, we're going to need an inverse matrix, realistically, but we got to understand what an identity matrix in multiplication is. If I said 5 times, give me your eyes, 5 times what gives me 5? You would tell me, what would you tell me? 1. 6 times what gives me 6? 6 times what gives me 6? Sorry. Oh, I thought I heard something weird in there. I was like, oh, good heavens. 9 times what gives me 9? Okay, so 1 is considered the multiplicative identity because it results in the same thing from beginning to end. The difference with matrices is you don't just fill in a whole bunch of 1s. It wouldn't play out that way. We'll look at that in a little bit. So what we just do is we clarify right out of the gate, and we say, okay, the idea of addition is that I add a bunch of zeros. The idea of multiplication is that I set up what we're going to call the identity matrix. If there is just a 2 by 2, it's going to look like this, 1, 0, 0, 1. The diagonals are 1s. The rest are zeros. And once we start doing this, it'll make more sense. And then here is when an identity matrix for a 3 by 3. Again, the diagonal is all 1s. All the rest is zeros. So, if you go to the next slide, or look at the next slide, we're going to clarify what it means to have two matrices be inverses. So you're going to have to really stick with this because it all goes back to just basic real number stuff. But if I told you 5 plus negative 5 is 0, which y'all agree with, right? Then I would say those are additive inverses. If I said, hey, 6 times what gives me 1? What would you tell me? 6 times what gives me 1? 1/6. 6 and 1/6 are considered inverses because they give you the identity. Make sense? Okay, so what do I need to do to these to decide if they are inverses? Multiply them and see if I get 1, 0, 0, 1. Okay? So all I want you to do with the people that you're working with is just multiply it out and compare it. Go. you're just going to multiply these out. Because if I say, hey, 6 times what gives me 1, you would tell me 1/6, right?
Yeah.
Okay, so if I told you, hey, are 7 and 1/7 multiplicative inverses, you would say yes. Why? Because they give you 1, right? Okay, you ready? Yeah, no. Take a second. Oh, yeah, go ahead.
I kind of got confused with this before. If there's 2 like columns in the first one, how do you multiply by like 3 rows in the second one?
Are you considering that 3 rows? It's a 2 by 2 and a 2. That's just fractions.
Oh, the fractions.
Yeah. Okay, got an answer?
You make matrices.
I'm going to show you tomorrow. Okay. Does anyone need me to walk through the matrix multiplication? Okay, so if you heard Ethan's question, and this is Alec asked it a minute ago, you actually can do this all on your calculator, and I'm going to show you how to do that. For now, are we okay with coming up with 1001? Okay, what can you conclude? Are A and B inverses? Yes, but here's the catch. In order to be inverses, both orders must result in the same thing. Rarely, if ever, I don't know that I've personally ever run into one working and one not, but you always have to check. So what I really need to do is do the other order. So in case I said that weird, to be clear, both orders, AB and BA, must result in 1001. The second one is usually just a check. But you should always run it. This is -2 plus 3 is 1. This is -4 plus 4 is 0. This is 3 halves minus 3 halves is 0. And that's 3 minus 2, which is 1. So we conclude, since both AB and BA result in 1001, then they are inverse matrices. So it gives you a little bit of clue as to what kind of question would be asked on your quiz on Tuesday, right? Are these inverses? Are you okay? Yeah, Malin.
So you just multiply them together?
Mm-hmm. Yeah, well, I multiplied the other order. Because remember, yesterday we looked at the fact that matrix multiplication is not commutative, right? So in order for an inverse, or in order for 2 matrices to be inverses, the order AB and BA must both result in the identity matrix. So I showed the first one, I just put it through to my calculator and, copied and pasted it. But the bottom one, I showed the second one. Okay? Okay, so you ready? There should be some questions kind of sitting in your head, like what about this? So one question that you might have at this exact moment is, well, how do I find an inverse? So, was anyone dying to wonder that? Thank you, Joey, I appreciate that. So, in order to find an inverse, we need what's referred to as the determinant. Now, that's not the same as the discriminant, so I always feel like those two terms get confusing a little bit. Discriminant's what's under the radical of the quadratic formula. The determinant, and it clarifies this here, the determinant of a matrix can be found by finding the product of, if I were to set up this 2 by 2, AD, and subtracting it from the product of BC. AD minus BC is the determinant. So, we're going to ignore this for right now, this bottom left portion. And right now I want you to find the determinant of, I'm going to keep it super simple, 2, 3, 5, and 8. Okay, so literally it is this simple. This is considered like an A, B, C, and a D. I'm going to have a determinant of this square matrix simply by taking the product of AD, which is what? Yeah, and for your own sake, if you want to one time write out, you won't need to do this every time, but if you want to one time write out all the numbers, that's 2 times 8 minus 5 times 3. That's 16 minus 15, which is 1. We would say the determinant is 1. Now, tomorrow we'll talk about the determinant of a 3 by 3. For now, can I move on? Do me a favor and find the determinant there in letter A. Go. And then just pop your hands up when you have it. Okay, got an answer, raise your hand. Good. What is your answer, Madeline?
17.
Why? Agreed.
Because it's 15 minus negative 2.
Yep. Feel easy enough? It is. It's meant to be easy. Okay. All right. So, well, why do we need that? Now, you're going to notice we're going to jump a little bit just because it'll make your homework more worthwhile tonight. The reason we need that is because we can use that to find an inverse. So, one way to ask a question would be, are these inverses? They are if when you what them, two matrices are inverses if when I what them, we just did a second ago. Multiply them, the result is the, what do you have to get? 1, 0, 0, 1. Two matrices are inverses when you multiply them together, the result is the identity matrix. The flip also has to be found, meaning how do I find the inverse that when they are multiplied together results in the identity? So since I can tell from your faces that you just cannot wait, we're going to fly through this problem. Ethan's face is just clear that he's super excited about this. So if I have a matrix, A, B, C, D, I can find its inverse. Notice the notation, similar to the notation you've seen before. By, now watch this, flipping D and A, taking the opposite of B and C, taking the determinant, finding the reciprocal of it, and multiplying it as a scalar. Don't let that confuse you. It's not hard. All you're going to do, if I want to find the inverse in example 4, is follow that same process. So, for a clean 2 by 2, I'm going to take the two corner ones and what them? Flop them. So this number is going to become what? 3. And this is going to become what? And I'm going to take these two corners and what them? Take their opposites. So this one is going to be what? And this one's going to be what? 1. On the outside, I'm going to take 1 over the determinant. So off to the side here, I'm going to need to find the determinant. What is the determinant of A? Just give me the numbers. You don't have to give me an answer. -9, I heard it, minus, what is that answer? Awkward silence over subtraction. -9 minus -6 is, thank you, -3. I take 1 over -3, and I treat that like a scalar, just like yesterday. So now I'm going to have that scalar go to each one of these elements. What is going to be the element in this 1, 1 spot? -1 here. 2. Here. Are we unclear? Like, this is about as easy as it gets. Thank you. We're just multiplying, right? What goes right here? 1. Okay, so, for the record, the question is, does the matrix have an inverse? We just found it. What would cause there to be a matrix that doesn't have an inverse? Can you see a problem with that formula? Yeah, Aaron. I legit cannot hear you. Okay, so Aaron's comment is about the size of the actual matrix. We're going to do these with square ones anyway, but I agree with you. Yeah, Ethan? Yeah. Here's the deal. I want you to add this in a bubble here. or actually add it more up towards the top. Add this comment, or at least circle this. If the determinant is 0, then there is no inverse. But I'm also going to put it in words the way Ethan just said it. If A has a determinant equal to 0, then there is no inverse. I suggest using, like, literally writing it down so that it sinks in. So the truth is, the second you get a determinant and you see that it's 0, you're done. As long as the determinant's not 0, you keep moving. Okay, so the last thing I just want you to do, and the answers are, I went ahead and let the answers show on this one. I want you to tell me real quickly, what is the determinant of B here? Don't give me, I mean, if you glance down and you understand this, you're going to know an answer, but actually give me numbers for me, please. How do you find the determinant there? Negative 20. What is that? What do I conclude? No inverse. Okay? I found the determinant. It's 0. No inverse. A, what is the determinant? 2. Find the inverse. Go. Okay, and the answer, I just went ahead and it shows there, so you can just go ahead and check it. Okay. Are we okay? All right, so I want to take a few minutes and just talk through, because we have 50 today, so I want to make sure I'm clear on what your homework is. At this exact moment, I did not check your 12-2, right? Tomorrow, I'm going to check a combination of the following. I could check your 12-2 that you just checked in class, okay? Also, tonight, and this will be on Schoology, but I want to make sure everyone is clear. On the same 12-2 worksheet, you're going to do 2 word problems, numbers 22 and 27. Now, that's only 2 problems. After that, listen to what you already picked up. You picked up this sheet that says additional vocabulary support. You picked it up the other day. I'm just going to label it ABS. You're going to do both of these. This content is not super hard. I don't feel the need to kill you with a million addition problems. But we do need to make sure we understand the ideas here and the different terminology, because obviously since this is new content, you've never seen it before. We got to make sure that you're clear on that. Alan?
Wait, so what is ABS?
Additional vocabulary support. And then on 12-3, which is what we just did, you're going to do numbers 2, 4, 5. 7, 10, 19, and 21. Now, some combination of those I will look at tomorrow, okay? I'm not looking at every one of them. I'll try to pick 2, okay? All right, any questions? Okay, so you also picked up the 12-1. It says 12-1 enrichment, and on the back it says 12-2. I'm going to actually talk through that a little bit more tomorrow. That's going to be a bonus. You're going to be able to turn that in on the quiz day. Okay? As a heads up, the quiz is going to be no graphing calculator. So I'm going to start showing you how we're going to use it next week. But you're allowed to use an OGT calculator. I'll bring a bunch in here. But just just as a heads up, no graphing calculator on Tuesday's quiz. Okay?
I slept through that one.
I figured. Okay, we're good. Thanks. The whole thing. It won't take you that long. Yeah.
Like both.
Yeah, front and back.